All right, I'm still working here in 13.2. Decided to go ahead and do some of these later problems. Here's number 40. I'm going to read the problem out here. The force exerted by an electric charge at the origin on a charged particle at the point xyz with position vector r is equal to the vector xyz is given to us by the force, the field, as a function of r is equal to k times r over the magnitude of r cubed, where k is a constant. Find the work done as the particle moves along a straight line from 2, 0, 0 to the point 2, 1, 5. So we want the work done, so we definitely want to compute the line integral over c of f evaluated at r of t dot dr. Now, we need to come up with a parametric representation for this line segment, and to do that, we've done this before, I'm going to look at r of t to be equal to, let's see, the starting vector 2, 0, 0 plus t times the vector that goes from here to here, so 0, 1, 5. And so this equals, let's see, 2, and then we get t, and then 5t. There we go. So there's the parametric representation for the line segment. And now what we want to do is we want to plug this into our vector field. So we're going to put it here and here. We'll have to take the magnitude of it and then cube it. But then we're going to dot it with dr. And dr is, let's see, we take dr, here's the derivative of r of t, which is just going to be 0, 1, 5. We're going to be dotting that, so that's that, dotting it with this dt. So let's go ahead and try and figure out what this is. So I'm going to do f of r of t will be equal to k times the vector r, which is 2t, 5t, over the magnitude of this, which is 4 plus t squared plus 25t squared. So that's the magnitude of it, but then cubed. But I'm going to dot that with this right here. So 0, 1, 5 dt. All right, so that is what we get. I shouldn't say that. This is f of r of t dotted with dr. So that's what we want here. We're going to set this up in an integral. T, of course, goes from 0 to 1. And that should be it right there. So let's see if there's anything we can do to help clean this up. Remember that k over all this is a constant. So we get integral from 0 to 1. Let me just dot these two vectors. This times 0 times 2 gives me 0. 1 times that gives me t. So I'm just looking at the dot product right now. Right now I'm going to get 0 plus 1 times t is t plus 5 times 5t is 25t. That's our dot product. And all of this, k over all this right here, square root of, I'm going to say 4 plus, I'm going to add those two together, 26t squared, all of that cubed dt. All right, so I hope you kept track of what I did there. This right here is a constant, right? So I dot two vectors and get a number or a scalar function. So this and this gave me this part, and then I just multiply it by this thing, which is going to be some constant. All right. All right, let me clean it up. Integral 0 to 1. K, I think I'll pull the K out. This is going to be 26t on top. And then underneath this, I've got, I'm going to say 4 plus 26t squared, all of that to the 3/2 dt. And I'm going to make a basic u substitution here. I'm going to let u be equal to the entire expression in here, 4 plus 26t squared. The derivative of that will be 52 t dt. And you can see here I have 26 t dt up here. So I'm going to divide both sides by 2. So 1/2 du is equal to 26 t dt. And so I can replace this part with 1/2 du. And I can replace this with u to the 3/2. So I'll get something like this. This is just the integral, okay? Just the integral without the 0 to 1, okay? So this k, I'll get a 1/2, like I said, a 1/2 du, so I'll put 1/2 du, and then 1 over u to the 3/2, which is really u to the negative 3/2, and then I do my antiderivative. So 1/2 k, add 1 to this, we get negative 1/2, flip it, so negative 2 u to the negative 1/2, and plus some constant. So this is really just negative k over the square root of u, which was 4 plus 26t squared. So that's the antiderivative. So this is going to become equal to negative k over 4 square root of 4 plus 26t squared, evaluated 0 and 1. So when I plug in 1, I get, let's see, negative k over square root of 30 minus, and then when I plug in 0, I get negative k over square root of 4. So this is going to become, what can I do here? Negative k over root 30 plus k over 2. Let's see if we want to clean that up at all. I think that's the way the book leaves it. They factor out a k, but this is good enough. One of the confusing parts of this problem is the fact that when they give you r, they say, okay, r is x, y, z, and that's somewhat confusing when you look at it. What they're saying is that your r vector, okay, is, if you look, imagine three-dimensional space, you're moving along some line segment, right, which, wherever it was, we're moving along some line segment, okay, and we had to find the parametrization of that line segment. But they're just telling you that the r is actually the position of where you are in three-dimensional space. It is the x, y, and z components of that line segment, which we got. So I think that's one of the more confusing parts of the problem is why do they write that? Just understand that all they want you to do is get the parameterization of this and use the fact that the x will be x, y will be y, and the z will be z in each of those parametric equations. All right, let's look at, let's see, 42 is somewhat interesting. So for 42, we have an object with mass m. Okay, so you have an object that has a mass of m, moves with the position function, r of t equals a sine t I hat, so I'm going to put that like that, plus b cosine t j hat, and then c t k hat, which is that. And it's on the interval 0 t, 0 is less than or equal to t is less than or equal to pi over 2. And they're asking you to find the work done on the object during this period of time. Well, problem here is that it's not just obvious that what the field is. All right, so we need, in order to compute the work, right, we need to know the line integral over C of the vector field evaluated on the curve, right, dot dr. Well, we know what r is, okay, so that's not a problem. We'll need its derivative, so may as well get its derivative here. That's going to be a cosine t, negative b sine t, and c. So a, b, and c there were constants. But what about the field? Well, what we can assume is that the field here we're talking about is a force because they're looking for work. So the vector field is going to be a force. Okay, the force vector is equal to mass times the acceleration vector. And we know from our study of vector curves that the first derivative represented the velocity curve, and then the second derivative would be the acceleration function. So what I need to do is take the derivative again, right, which would be the second derivative of our position. So take derivative of this with respect to t, we get negative a sine t, and we get here negative b cosine t, and then 0. So now if I'm trying to find my force, right, my force vector will be the mass times the acceleration, which we just found to be negative a sine t, negative b cosine t, and 0. And if I go ahead and multiply the m through as a scalar multiplication, just distributes, I get finally that my force vector, okay, is going to be equal to mass times this, so negative a times mass times sine t, and then mass times this, you get negative b times mass times cosine t, and then mass times 0 is still 0. So you just get 0 here. So there's my field, all right? And I don't need to plug in r of t into it, right? I don't need to plug r of t into it because this entire thing, right? This entire thing, you can see up here, is a function of t now. And the way we got it was using the fact that the field would be mass times acceleration. So I don't need to plug in, and it wouldn't make a whole lot of sense to plug in this into this, right? Like, how are you going to plug this in here? But you can kind of see it already. I mean, it's there. It's this is like the a sine t, and the b cosine t is there, and then the constant. Well, the fact that the acceleration was 0 wipes it out. So that's it. We just need to take that and dot it with r prime, which is this one. So this work will be equal to integral from 0 to pi over 2, because that was my restriction on t. This right here, which was negative a m sine t, and then negative b m cosine t, and then 0. And then I'm dotting that with the dr, which is this. So I'm going to run out of room. I think what I'll do is I'll rewrite this up here. So my work is going to be this from 0 to pi over 2, right, dotted with dr, which is this one, a cosine t, negative b sine t, and c dt. and then go ahead and do the dot. So let's do this. This will be equal to the integral from 0 to pi over 2. Okay, this times this, we're going to get negative a squared m sine t cosine t plus, now this times this, negative and negative is positive, so plus is fine, b squared m sine t cosine t, and then plus this times this is 0, so nothing, and then dt. So now we have some choices here. Let's pull out the sine t, cosine t from both of these. So if I do that, I get integral 0 to pi over 2. Okay, if I pull out sine t, cosine t from both of those, I'll be left with a negative a squared m, and I'll be left with a plus b squared. So I'm going to write that backwards. B squared minus b squared m, sorry, minus a squared m, and then sine t cosine t dt. So since I'm integrating with respect to t, I don't even need to worry about that. The antiderivative of this is going to be, let's see, b squared m minus a squared m, and then times 1/2 sine squared t. So I just did a quick little u sub. This is u, that's du, so this is it. Evaluated from 0 to pi over 2. Then we plug in. Sine of pi over 2 is 1, 1 squared is 1, and then times 1/2, and then times that. So I just get 1/2. You know what, I'll factor an m out also. 1/2 m, b squared minus a squared, and then when I plug in 0, sine of 0, 0, kills everything off. So you just get this. So that should be the work done. Which one was that one? 42. So I guess what I can stress to you again here is work, you know, was the line integral c of f dot dr. I mean, that's what it is, right? Now, if we come up with the parametric representation for the curve c, then we have to plug that into the vector field, right, in order to figure out what this f is. But for us, we didn't have to do that. To get f, we used the formula of mass times acceleration. So really, we're replacing this with this. It wasn't necessarily us trying to plug the curve into the field, right? We knew what force was, so we didn't have to think about it this way. All right, and then let me see, 43 is very much like one I did in class. So that was a man carrying a bucket of paint up a silo, okay? So, you know what, I'll look at number 43, and then I'll look at 44. So 43, you have a 160-pound man. He's carrying a 25-pound bucket of paint up a silo, up a helical staircase with the radius of 20 feet. So you have this silo. It has a radius of 20 feet, and it is 90 feet high. So what we did is we tried to come up with a way to parameterize that curve. Okay, you start off here, and it goes around 1, 2, I believe it said 3 or something like that. 3 times? Yeah, 3 complete revolutions. All right, so yeah, I think this is almost exactly like we did in class. So what is the force? First of all, the only force we have at play here is gravity, and it's acting, you can look at it 2 ways. You have gravity going down, which we could say is a negative force, or you could say the force of the man going up, countering the gravity. So we can look at the forces being either straight down or straight up. it won't matter. I'm going to look at it as being straight up. So a vector that goes straight up is going to have 0 for the x and y components, and then the force up would be 185. Okay, like that. Remember, pounds is a measurement of force, right? Pounds is a measurement of your mass times the acceleration of gravity. In other words, weight is a force. And now I need to come up with parametric representation of this curve. So the way we did is first we drew a circle with radius r, okay? So that was 20 cosine t, 20 sine t. But then we need to go up, and we need to go, well, I should say it this way. T right now has to be between 0 and 6 pi, because I want to do 3 full revolutions. So this will draw me a circle when t is between 0 and 2 pi, so I need to go around 3 times, so I need to go from 0 to 6 pi. So that draws me 3 revolutions, and in that time, when t varies from 0 to 6 pi, I need to only go up 90 feet. So if I write 90 over 6 pi t, that will be my z component, right, at t equals 0, right? T equals 0 here will be on the ground. And when I finally get to 6 pi, 6 pi cancel 6 pi, you'll be at 90. And it's linear, so you're going to go from 0 all the way to 90 linearly, which is the same thing that would happen if you look at someone going up the stairs. The z component is linear. All right, and then we did derivative here because we need dr, so negative 20 sine t, 20 cosine t, and this is just 90 over 6 pi. And so we're going to take our force and we're going to dot it with this, and then we're going to go ahead and get our integral of that. So when you dot these two together, what's nice is 0 kills this, 0 kills this. All you get is 185 times this. So all we're going to do is do the integral from 0 to 6 pi of 185 times 90 over 6, 90 over 6 pi, and then dt. And the antiderivative of that is 185 times 90 over 6 pi t evaluated from 0 to 6 pi. And when you plug in 6 pi's cancel, you get 90 times 185. 185 times 90. And then minus, when you plug in 0, you get 0. So 185 times 90, which is about what the heck? Oh, they rounded. Okay. This is about 16,650. And then the measurement here of work would be done in foot-pounds, because everything was measured in pounds and feet. Okay, so that's number 43. Now let's look at number 44. In number 44, they want us to do the exact same problem, except there's a hole in the can of paint, and 9 pounds of paint leaks out of the can during the ascent. So as the guy goes up, right, as he goes up, his as he goes up, the silo, the force changes because his weight's changing, right? So remember, we have 100, how heavy was he? 160-pound man to start. Then you had a 25-pound bucket. And 9 pounds of paint should leak out through the entire trip steadily, so linearly. So when we look at our force, our force is now, we still have 0, 0. Okay, that doesn't change because our force is either straight down or straight up, again, depending on which way you want to look at it. But the force is changing in the z component. It's the original 185, but by the time he gets to the top, he needs to have lost 9 pounds of stuff. And remember that our t is going to vary between 0 and 6 pi. So we need to subtract from this. We need to be at 9 at the top, right? We need a total of 9 to be taken away and nothing to be taken away initially. So it's kind of like what we did earlier, except I'm going to go 9 over 6 pi t. So if t is 0, hold on. Hold on a second. This is, t is 0. We need to have, you know what, let me see. There's a couple of ways you can approach this. Yeah, if t is 0, you're at 185, right? T is 0, you're at 185, so that's him starting up. And as he goes up, paint starts flowing out, right? So the weight is changing. And when I get to 6 pi, they'll cancel, and I'll have 185 minus the 9 pounds. So we will have lost all 9 pounds of paint, and it will be linear, and it happens through the whole time interval from 0 to 6 pi. So this, I shouldn't say time interval, this is our angle, but we can look at it as time also. So this is basically the same problem. The only thing is that dot product at the end, remember when you do your dots, that last piece we had for r of t, this was r of t, it was something, 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 and that last one was 90 over 6 pi t. Then when we took the derivative, right, this became just this, and then we dotted. So this will go integral from 0 to 6 pi. We dot these, okay, the zeros kill off, that's why I didn't write them. Then over here, this times this, that's a little bit different, right? So we're gonna have 90, I can take the 90 over 6 pi out. I don't need it. And then I can have the 185 minus 9 over 6 pi. Yes, I could have reduced that t dt. And that's going to be a different answer, right? Because you're going to have to integrate this with respect to t. You get 185 t. Integrate this, t squared 2, so you should have minus 9/12 pi t squared. Right? That's the antiderivative of each of those. And then you have a constant out front. You're evaluating from 0 to 6 pi. So when you do that, and I don't think I'm going to do it, you should get Sixteen 245 foot-pounds. So you can see there's quite a bit of difference there because you've lost paint. You didn't have to do as much work. So you have less work done by this guy than the previous problem. But he's lost paint, so he's going to have to go back down and get more.